ॐ सहना भवतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, last time we discussed some aspects of ternary compound semiconductors and some applications. Okay. Today we will continue on that, because there are a few more things which we want to touch upon. This diagram in our last discussion we have put, I am putting it back again to refresh your memory on that. You can see here we have seen already discussed this. Y axis the band gap, energy band gap, x axis lattice constant and wavelength. We have also pointed out that the wavelength is related to the energy through a relation lambda is equal to 1.24 divided by energy. So, as the energy goes up, lambda goes down. Okay. So, if you want shorter wavelengths, you must have higher energy band gap, because shorter wavelength has higher energy, E is h nu. So, okay. So, now what I just did not point out last time was this axis there, that is a lattice mismatch. Okay. That is referred to with reference to silicon it is put. Everywhere it is put in terms of silicon, because silicon is the ruling king in the microelectronics today. So, if I want to see with reference to silicon, what is the status? See, for example, silicon 0 lattice mismatch, that is lattice constant is 5.45 or 5.43, also 5.43 for other material. For example, you can see right on the top here gallium phosphide is there, which means I can arrange gallium phosphide on silicon. I can grow gallium phosphide without hurting, without noticing any or without having any defects. I can grow gallium phosphide. That is the meaning of that. Epitaxial layers, layer one over the other. Epitaxy is a term used for arranged upon. You can arrange atoms the same arrangement as the substrate, provided lattice constants are same. Now, look at here gallium arsenide. It is about 5.65 lattice constant. So, that is about 4 to 5% lattice mismatch is there. So, it makes it difficult to grow gallium arsenide on silicon. We would have been very fortunate if we were able to grow gallium arsenide on silicon, because then you can have silicon for many of the microelectronic devices. You can have gallium arsenide for high speed part of it, or also optoelectronics part of it. That would have been something which would have been very fortunate. Unfortunately, it is not so, but still there are a lot of efforts which have been put forward to grow gallium arsenide on silicon. People have done that, not with great success, but some to extent some degree of success. One of the persons who has been trying, or with whom the work was going on, was the legendary figure on compound semiconductors, Saurabh Gandhi. Okay, he was the one who way back right from 1970s started working on growth of gallium arsenide. Okay. He was trying some of those work. Now, he retired of course, but still some work continues on that. Now, you can see some other material, gallium arsenide. If you want, on that you can grow aluminum arsenide, or compounds of aluminum gallium arsenide we saw yesterday. Oh, you did not see it actually, we saw gallium phosphide and gallium arsenide. So, you can match, you can grow aluminum gallium arsenide compounds on gallium arsenide, because as you vary add aluminum onto gallium arsenide, it becomes moves towards aluminum arsenide, but the lattice constant is same, because tetrahedral radius of aluminum is same as the tetrahedral radius of gallium. Arsenic is common, so the lattice constant is same, practically same. Because if you take argue, some people may say a slight mismatch still, but it is almost same. Now, this is what I did not mention last time, but you can, if you want to grow on silicon, it is difficult. You can see indium phosphide mismatch is much more. It is hopeless situation if you want to grow indium phosphide on silicon, but you can, you have, if you, in case you need, you have another material which is a composition of, that is a ternary compound, gallium arsenide and indium arsenide. If you mix, it becomes gallium indium arsenide. We started on that yesterday. I had rushed through yesterday, but today we will take a detailed look into the thing. So, there what happens is, if I adjust the gallium concentration, okay, and make it adjust some value, I can get gallium arsenide, gallium indium arsenide lattice match to indium phosphide. That is a very useful material. Okay, that is what we want to see today, and we will also see today when you mixing aluminum to gallium arsenide, aluminum gallium arsenide. These two are very powerful or very useful ternary compounds. Okay. So, that is what I was trying to point out. This is actually the energy gap on the y axis, versus x. X is the gallium mole fraction. If x is equal to 0, if x is equal to 0 there, oh, this is actually should be gallium, not G, Ga. Okay, just correct it. This is Ga. In fact, I suppose I can correct it right there. Okay. Yeah. So, this is the, okay, that is GAA, gallium indium arsenide. So, now if x is equal to 0, gallium is 0, you get indium arsenide. I am probably repeating some aspects, but since I went hurriedly in the last minute yesterday, today I am just going through that. X is equal to 1, that is 0, the total is gallium arsenide. Now, the both are direct band gap. So, you mix them together for whatever is the composition, you must get direct band gap. You can use it for photonic applications, optoelectronic applications very easily, because the transition of electrons can be met with by emission of a photon, light. So, the band gap here is 0.36 electron volts for indium arsenide. Band gap there is actually 1.43, you know, I have not put it again here, 1.43. Okay. Now, if you mix it such that x is equal to 0.47, gallium is 0.47 and indium is 0.53, then what you get is actually gallium indium arsenide with a composition gallium 0.47, here 0.53. Okay. That particular compound has got a band gap of 0.75 electron volts, and 0.75 electron volts corresponds to 1.24 divided by 0.75, that is actually equal to 1.653 microns. What is so great about 1.653 micron? Supposing I make a diode, it can be used as a detector. Okay. It can be used as a detector for wavelengths up to that particular thing. Okay. Supposing you saw that, let me just write on the board here, wavelength lambda is equal to 1.24 divided by E, so many micrometers, provided E is in electron volt. Okay. So, there is a direct formula which comes up as a result of the relationship E is equal to h nu. Now, if E is equal to 0.75 electron volt, okay, then lambda is equal to, the wavelength is equal to 1 point, from this formula 1.653 micrometers. The question is, what is the meaning of this? The meaning of this is, for example, if I have the band gap, that is E c minus E v is 0.75 electron volts, okay, then the photons having energy, okay, the photons having energy greater than 0.75 electron volts will be absorbed, creating a hole, that is plus charge, and an electron. So, the photons having energy greater than 0.75 electron volt will be absorbed, creating a whole electron pair. Now, the wavelength of these photons corresponding to this 0.75 electron volts is actually 1.653 micrometers. If the energy of the photons is less than 0.75 electron volts, it implies that the wavelength of the photons is actually more than, energy is less than 0.75 electron volts, means lambda is more than 1.653 microns. What we are saying is, if the photons have energy less than 0.75 electron volts, it will not be able to raise the electrons from the valence band to the conduction band. That means, the photons will not be absorbed. So, what we are telling again is, if the wavelength is, if the energy is less than this, the wavelength is more than that, and the photons will not be absorbed. And what will happen to those photons? The photons will actually be not be absorbed, it will be just transparent. It will not go, it will go through the material completely. Now, so if we say 1.653 is the wavelength beyond which it will not be absorbed, what we imply is the absorption coefficient or absorption, okay, the absorption if we call and versus lambda in micrometers. What happens is, till the wavelength is equal to 1.63, there will be 100% absorption of the photons. That means, it will create whole electron pairs. Whether it give rise to current, it is a different matter. So, it will create whole electron pairs till the wavelength is 1.653 microns for this situation. Okay. So, longer wavelengths will not be absorbed, it will be just be transparent. Now, why are we so much particular about this particular wavelength? What we are saying is, this particular wavelength, within this wavelength, or the photons having wavelength within that particular value are used in the optical communication, fiber optics. There, the lambda that is used for communication purpose is 1.3 microns or 1.5 microns, because at 1.3 microns and 1.5 microns, the attenuation is minimum, and also dispersion also is minimum. So, because of that, they should be able to use a detector which will actually absorb wavelengths of about 1.3 microns or 1.5 microns. So, if the wavelength is 1.3 microns, somewhere here, okay, absorption will be 100%. So, that means, this particular material, gallium indium arsenide with gallium X, indium 1 minus X, arsenic, that material can be used to realize the detector, provided X is equal to 0.47. There is a mole fraction of gallium. If it is 0.47, it can be used for making a gallium indium arsenide diode, which will actually respond to the wavelength which is within this particular value. And in optical communications, they use this particular wavelength of 1.3 and 1.5 microns. That is the two windows that they are using. So, this is a very useful material for making the diodes for fiber optic applications. Instead of gallium indium arsenide, if you use gallium arsenide, then the cutoff wavelength is much smaller than that, because the band gap of gallium arsenide is 1.43. So, the lambda corresponding to 1.43 electron volts is 0.87 microns. So, what we are telling is, if you make a gallium arsenide diode and if you use it as a detector, that will actually stop absorbing, absorption versus lambda. So, for gallium arsenide, if I plot, that will go like this, that is 0.7, that is 0.87. Okay. So, if the incoming photons has energy wavelength 1.3, it will not get absorbed in that particular thing. So, that is why gallium indium arsenide diode should be made for realizing a detector for fiber optic applications. So, what we will see is how this can be made use of to absorb and generate current. That part we will see by realizing, showing how a diode can be fabricated, or how a diode structure schematically how you can make with gallium indium arsenide p-n junction. So, you make a diode, you make a p plus n diode made up of this material, both. Okay. I am just showing a schematic diagram. Shine light, which actually is that 1.3 wavelength, for if you are connecting a fiber onto that, which is just about 10 micron uncladded, including cladding it will be about 120 microns. So, that you connect it to that, align it to this junction, then what would happen? You also have to bias this, reverse bias it. So, what you the whole idea is, the whole electron pairs which are generated should be separated, and when you separate them, current flow will be there in the external path, like the solar cell. Okay. So, supposing this falls here, from there we know if this is 1.3 microns wavelength, definitely whole electron pairs will be created. Now, when it is created, they are in the vicinity of each other. If nothing separates them, they will recombine in the vicinity of each other. So, what you should do is, the whole electron pairs must be generated in a region where there is an electric field, that is the depletion layer. If you take a look at this this particular region, I just put a light color here. That is the depletion layer. Now, if this falls on the depletion layer, what is the fate of these whole electron pairs which are created? Where is the electric field? Plus here, minus there. The polarity of the voltage is like this, the electric field is in this direction. E is the electric field. I am going a bit, okay. Let me put it on the other side. So that it is visible clearly. So, this is the voltage that you are applying reverse bias. Okay. Now, E is the electric field like this, okay. So, this electric field is plus here, minus there. So, the whole electron pairs if they are generated here, they have no time to recombine, because before they decide to recombine, this electric field pushes it in this direction, this pushes in this direction. So, if you take any cross section, if you take this cross section there, it is only the hole which is giving rise to current. If you take on this side, it is only the electron, it is only one charge, either hole or electron, plus q or minus q. Either way, the current flow direction is the same. Hole moving in this direction gives rise to current in that direction, electron moving in this direction gives also current in that direction. So, in the external circuit you have current in this direction. I photon, current due to the photons. The current due to the photons, okay, if 100 photons are impinging, you will get 100 whole electron pairs giving rise to current, provided all of them are generated within that. If they are generated outside here, the chance of it being collected in the external circuit is 0 or small. Okay. So, then if out of 100, if 30 of them or if 50 of them fall here within this region, the photons, those 50 of them will not be giving rise to current, because they will recombine. So, the quantum efficiency, which is the number of whole electron pairs which are available for current flow, divided by number of photons, that is the quantum efficiency. Whole electron pairs divided by number of photons, but that is the quantum efficiency. Whole electron pair not generated, whole electron pairs which are available for current flow. If they recombine within there, no point. So, that is the quantum efficiency. Okay. It is a jargon term used by physics people, but ultimately it is how much current flows for so many photons which are impinging. That is the ratio, it is a figure of merit. Okay. So, this is the situation now. Now, the problem in this type of structure is, what is the problem? This layer, if it is thicker, what will happen? Most of them will fall here and most of them will recombine, and the current will be very small. Sensitivity of this detector will be small. You will, okay. So, you have to optimize this thickness, you must reduce it. You must have a finite thickness, no doubt. You can't, you have at least 0.1 micron, 0.2 microns, within which quite a bit will be absorbed. So, you can't say I will make it 0, 0 means no junction. Okay. So, the key thing to do it is use your ingenuity, come up with another semiconductor from the back side and inject light from the back side. This will be very powerful technique. That is what we said, what we are trying to mention yesterday. So, to avoid recombination in this layer, what you do is you change the entire structure now. Okay. That I will show here. This diagram is the diagram of the detector. Instead of making the entire p-n junction with gallium indium arsenide, what you do is use a substrate which is indium phosphide, n type, use a p type region, indium gallium arsenide, gallium indium arsenide. See, instead of making a p-n junction both of indium gallium indium arsenide, you make a p-n junction consisting of gallium indium arsenide layer and indium phosphide. Let us see what does the indium phosphide do. So, notice here, instead of shining light from top, in this case you are connected on the back side the fiber. The blue thing is the fiber. You have connected that on the back side, light is connected to that. In fact, I have shown it small because that fiber is just about 10 microns, 9 to 10 microns single, okay, uncladded, but when you clad them it may be 120 microns. So, that is what is connected there. Now, what happens to the light which is coming here on the back side? See, a junction now is here, this is a p type and this I have marked it as new layer. What is new layer? New layer is n layer, very lightly doped, very close to intrinsic. Yesterday I wrote it as intrinsic deliberately because I did not want to confuse the issue at that time. It is actually a very lightly doped region. So, if you have very lightly doped region, what happens? This is p plus, this is n layer. The depletion layer will be occupying completely this layer. Take this n layer doping something like 10 to the power 17, does not matter, and take this as 10 to the power of 19 or so, and this is very lightly doped. So, if I reverse bias that, make this negative and this region positive, like this, positive and negative. Here I have got on bottom side indium phosphide, and on the top side instead of p layer I have got p plus and a new layer, and new layer is very lightly doped. That layer can be a micron. Now, what happens when a wavelength comes into this? Let us see that. So, let us see what happens. Indium phosphide, what is the band gap? 1.35 electron volts. What is the cutoff wavelength? Lambda corresponding to that is 1.24 divided by 1.35 micrometers, which is actually equal to 0.92 micrometers. What does it mean? If I have lambda versus absorption, up to the wavelength of 0.92, energy is greater than that. Smaller wavelength, larger energy. So, it will go like that. And okay, and at lambda equal to 0.92 microns, beyond that point, if you have light falling wavelength, it will not absorb. Okay. That is, it is transparent for wavelengths greater than 0.92 micron. Now, this wavelength is of no interest for you. So, if I use indium phosphide here on this side, okay, and if I have light of whatever wavelength comes in, till the wavelength is about 0.92, it will be absorbed here, okay, because the energy is greater than 1.35 electron volts. It will be absorbed in this layer, and if it is a thick layer, 200 micron thick layer. So, if it is absorbed there, it is lost by recombination. Okay. So, if you do not care about those, in fact, this is very good. If there is some other light coming, it is suppressed there. So, up to 0.92 microns, this will be absorbed. Beyond that point, if the wavelength is more than that, indium phosphide is transparent. That means, this layer is as if this layer is absent, as if this layer is absent. When the wavelength is more than 0.92, the light goes through all the way and hits this lightly doped new layer, and that lightly doped new layer is depleted. Why is it depleted? Doping is very low concentration, depletion level 1 micron very easily can get. So, the entire this red color there, that portion that is red, that is depleted, and the electric field is actually in what direction? From in this direction, from bottom to top. That is the direction of electric field. So, when it wavelengths which are greater than 0.92 microns will reach and hit this, and once it hits it, it generates whole electron pairs, because that can absorb. The window for that is for the, this is for indium phosphide, and for indium arsenide we saw what was the thing? It was like this. I will put it right across that. That is the cutoff. So, this is 1.65 microns. 1.65 microns is the cutoff point for the indium phosphide. Gallium 0.47, indium 0.53, that one. Now, can you tell me, if I have bottom layer consisting of indium phosphide and the top layer consisting of gallium indium arsenide, if the light comes in from bottom up to this wavelength, it will not reach that. It is not reaching that because it is absorbed right here, but beyond that 0.92 it will be absorbed here, which would mean I have actually a window current. So, whatever is generated here will give rise to current, because it is electric field. So, till that point, till lambda equal to the I photon for this diode, what we are showing detector will be till lambda equal to I will put it here 0.9, up to that there is no current, and I will put it as 1.65. So, you will have 0.92, up to that it is absorbed by the indium phosphide layer, no current. So, beyond that point it will start coming up like this, okay, gradually pick up there almost steeply like that. So, the I photon, in fact, this will be about 70% quantum efficiency. QE is quantum efficiency, current generated due to one photon, 100 photons are generated in that layer, some of them escape, okay, which are just generated near the edge. So, you get about 70%, that is 70 whole electron pairs are created and all of them gives rise to current. Okay. So, that is the meaning of that. This is actually a window. So, you have a window right from about 0.92 to 1.6 micron, where you will get the current, it will be sensitive to that. This is very powerful technique for using for device for use in fiber optic application, where you need some air here within that region. If you want 1.3 or 1.5, this can be used. In fact, I am happy to say, Appl announced that in the EE department in our microelectronics laboratory, a device has been made like that with gallium indium arsenide on indium phosphide. You need to actually do a lot of passivation work, etc., in that, which may come up when I discuss later stage in this, when I talk about little bit of technology. Okay. So, that sort of device has been made, including connecting this fiber on the back side. You etch from the back side, so that the fiber is connected onto that. In fact, I was trying to get one device today, but somehow I was not able to, because they had handed it over to the company which wanted it in Hyderabad. Because we made just a prototype, just few of them, and handed them over. They are very happy. Now, the signal output that you get there, okay, the current to the diode, that can be that will be quite large, but still if you want amplification, you can put amplifier. So, what people would like to do is the detector and the FET amplifier together can be put together. That is something which we are looking into now. Okay. So, this is the idea. The idea of putting the indium phosphide layer on the substrate is, now what is the benefit that you get? You do not have to worry about this particular junction depth, because you choose this about a 1 micron, from when it comes from this end right up this, within that 1 micron almost everything is absorbed. Okay. If it is not absorbed within that, little bit loss will be there, that is a small loss that you get. So, that is the key, you do not have to worry about the thickness of the junction there. Okay. And this layer, presence of indium phosphide, automatically decides the moment the wavelength is more than 0.92, it is available for whole electron pairs in this layer. This is a very powerful technique. Okay. Now, so this is all that I have said today, that is, we have written those things about the band gap, lambda of 0.92 micron, photons with energy greater than 0.75, okay, which will be absorbed by the I layer, that is lambda in this region, below that will be absorbed, you get that thing. Without the slide, I have just mentioned with the help of board there. Now, okay. So, that is the plot, which you do not have to do, because this is already available to you now. So, lambda micron 0.9, then that is about 70% quantum efficiency, and quantum efficiency definition is put there. Photon current divided by Q, I photon, the current that you get in the external circuit divided by Q gives you number of whole electron pairs. Please note, it is pair, because the whole electrons are separated. So, it is only one particle which gives rise to current in any cross section. So, that is why you have got that current divided by Q gives number of particles, number of pairs which are made available, divided by power, the optical power divided by h nu, that gives you number of photons. Total power divided by total energy or power divided by the energy of one particle gives you number of photons. So, that is the quantum efficiency of a detector. In a LED, it will be other way. You talk of how much current flows and how many photons are emitted. that you call it as quantum efficiency. So, quantum efficiency would mean whether you talk of emission or detection. These are detectors. So, this is in summary of this. Actually, it is a very popular detector in fiber optic communication, because you are looking for detectors in that particular wavelength, that window where it is about 1.3 microns wavelength. Okay. And it acts as an excellent window and absorbs the photons in the range 0.92 to 1.6 microns. So, that is about that particular compound which we have been discussing. We go back to this original slide here. This is the one which, you know, about when there were lot of work was picking up on compound semiconductors. Whichever conference you go, this is a slide. This slide was projected and 5 minutes spent on that. So, we have spent actually more than 5 minutes here, because we want to get a greater look into the thing rather than flashing it and taking it off. Now, so we have first said this material yesterday, gallium arsenic phosphide, okay, for light emitting diodes, and we have seen this portion where you have gallium indium arsenide lattice matched to indium phosphide. So, you can grow gallium indium arsenide by epitaxial technique, arranging atoms of gallium indium arsenide on indium phosphide is perfectly matched. You can make the detector. Okay. Such wafers are available commercially. If you want, you can buy P plus nu made up of gallium indium arsenide on indium phosphide, you can buy that. In fact, when we made the device, we bought that and etched and made all the contacts, etc. Okay. Now, the other one that is very popular, the first of those compounds which people were looking into was gallium arsenide lattice matched to aluminum arsenide, and you can see gallium arsenide is a direct band gap material. If you keep on adding aluminum, at that point onwards, from that arrow point, you see the dotted line saying that it is indirect band gap. So, you have got direct band gap switching over to indirect band gap beyond a certain point. Okay. Now, the nice thing is any composition of aluminum gallium arsenide is lattice matched with gallium arsenide, because the worst case is gallium is 0, that is matched. So, any other combination is matching with the thing, mismatch is practically 0. Okay. Now, let us see that compound consisting of this, and band gap you can vary from 1.43 right up to 2.26, but changing from direct to indirect. Next slide, if you see, that is the one, aluminum gallium arsenide, AlGas. Okay. This is another term which people can use, saying if you take a lot of time aluminum gallium arsenide, you say AlGas, do not stop with AlGas. Okay. So, now here the red color, or if you take gallium arsenide, it has a direct band gap at 1.43 electron volts. It has an indirect band gap at 1.8 electron volts. I hope you are able to recall that. If you see the energy band diagram to recall, okay, what we mean by putting those two are, to just to recapitulate your memory, electron volts, 1.8 electron volts. Okay, that is the energy versus momentum, that is the conduction band, repeat again valence band. So, that is what we projected there, 1.43, red color is direct band gap and the green is 1.8. If you take, that is gallium arsenide, that is x equal to 0 gives gallium arsenide, x equal to 1 gives you aluminum arsenide, and aluminum arsenide has got actually I think that's got missed out, that should be removed from there. Okay. that is point, I think somewhere it has come from. Oops. See, you can correct it here. See, what is happening is this particular thing is not there. Okay. So, what I am trying to point out is you have got 3.02 electron volts there, okay. That is like this. This is gallium arsenide. Aluminum arsenide has got a 3 point, that there is a direct band gap is 3.02 electron volts. Okay. I must draw it even bigger than that because it is bigger than here. So, that is 3.02 electron volts. Okay. It has also an indirect band gap. I just did not put it down there, which is actually equal to 2.168, something here. In fact, this point here should show 2.168 here, 2.168. Okay. So, that is 2.168 electron volts. So, as I pointed out yesterday, when you vary when you change, so what you are looking for now is aluminum, gallium, 1 minus X Al gas, correct. So, this quantity is actually equal to X equal to 0, this quantity is X equal to 1. When you vary X equal to 0 to 1, okay, this which is 1.43 keeps on increasing to 3.02 finally. That is what is plotted there. And the indirect band gap, which is 1.8, keeps on changing, coming to, in fact, this is not same scale, 2.18. From 1.8 it will go to 2.168, that is this one, okay, 1.8 to 2.16. Now, at x equal to 0.3, both of, and this is almost linearly varying. At x equal to 0.3, okay, both of them become equal. That is, from x equal to 0, that is gallium arsenide to aluminum gallium arsenide with x equal to 0.3, if you go up to that point, that is indirect, this is direct. So, the material is in this region, see here. Here this is smaller than that. So, that is direct band gap. Here this is smaller than this, that is indirect band gap. So, if you go as you keep on increasing x, okay, this becomes wider, this also becomes wider, but to a less extent. So, they finally become almost equal. So, up to this point, red, that is a direct band gap, is smaller than the indirect band gap, which means it is a direct band gap material till x equal to 0.3. So, if I say Al gas, gallium arsenide Eg is 1.43, direct band gap. Okay. Direct band gap. Gallium point, I am sorry, x equal to 0.3, which would actually aluminum 0.3 mole fraction, gallium how much? 0.7 arsenide, Al gas. Okay. That is equal to, for this, Eg equal to that is 1.93. So, you can see I can get at this direct direct equal to indirect, you can call up to that point from 1.43 to 1.93 electron volts, you get a direct band gap semiconductor. If you want to choose, you can choose that for optronic applications. But beyond that point, if you increase the aluminum mole fraction more than 0.3, the band gap will go up from 1.93 right up to 2.16, 2.168 electron volts. It will go right up to that point. But the whole thing is green color here. Green is indirect, red is direct. Oh, that's okay. So it will become indirect semiconductor. This is actually a very popular semiconductor which has been tried out for years together. Okay, I think Kromer got the Nobel Prize related to something related to this, heterojunctions, etc. Now, okay. So this is just to illustrate, you can get a band gap varying, you can engineer the band gap, you can make it direct to indirect, all those things you can do. Now let us see. What are the different applications of it? Why are we taking a look at this aluminum gallium arsenide? If you can vary the band gap, what is the consequence of that? Where is the most powerful application? One of the applications, of course, in the optoelectronic applications. Okay. See, what happens is it is a direct band gap up to 0.3, you can use it for optoelectronic applications. Mostly this material is used up to 0.3, x equal to 0.3, because beyond x equal to 0.3, when the aluminum concentration becomes more and more, the material becomes sort of unstable. That part I am not touching upon, but up to 0.3 it is most welcome and people are using it, it is manageable material. You must be not only be able to do band gap engineering, you must also be able to manage the material, growing and seeing whether material is stable or not. Okay? So, up to 0.3 is direct band gap, very stable material and a perfect lattice match onto gallium arsenide, that vertical line you saw, which means you can grow aluminum gallium arsenide layers on gallium arsenide. That means you can make heterojunctions using L-gas on gas. You remember in indium phosphide, if you want to make heterojunctions, what material will you use? Gallium indium arsenide, because the lattice match of indium phosphide we saw is with gallium indium arsenide. Okay. That is where the heterojunction is made there. One application we saw. Here you can use L-gas. The nice thing about this is band gap of L-gas, aluminum gallium arsenide, is more than that of gallium arsenide. 1.43 there, that is right up to 1.93. So, you have no worry about leakage currents, band gap is larger in the case of L-gas. So, it is a perfect lattice match and these heterostructures are very popular for different applications. One of them is for laser. In fact, in laser what you have to do is, it is a p-n junction again. It is a p-n junction. You make a p-type material with the aluminum gallium arsenide, okay, and n-type region with the gallium arsenide, like this. Let me remove that. Not exactly n-type material gallium arsenide, it is like this. Very popular structure for laser. It is like this. P-type gallium, P-type L-gas. Let me draw that a bit bigger. See, laser is also a diode only. Okay. See, the diode is so powerful, it will haunt everybody in microelectronics, optoelectronics and everywhere. So, you have got like this. This material you can use as gallium arsenide, P-type. This material you can use as aluminum gallium arsenide within the 0.3 x within 0.3 P-type. This you can use it as aluminum gallium arsenide, n time. Okay. Now, what happens is this material is a wider band gap material, this material is a wider band gap material, and this one is like this E c and E v. I am just giving you just a flavor of this, that is all. Here there is a notch. If you forward bias this device, pump in current, okay, then of course it will bend, and you will have the electrons injected from here, they will be trapped there, they can be forced down to recombine. So, you have got a notch in which it will capture those electrons, and those electrons injected from N region to P region, forward bias p n junction will inject electrons that will be trapped here. It will not be going into the P region, and it will be available. And once it is available there, it will lose its energy to this side, and the laser wavelength corresponding to gallium arsenide you will get, that is 0.87. So, this is one of the applications, heterojunction, aluminum gallium arsenide. Other application of course is what we are going to spend a lot of time on, that high electron mobility transistors. Okay, the high electron mobility transistors, HEMT. Again I am just showing you the application, that is all. Okay, this is P gallium arsenide. Okay, on the top of that you will have Al gas. Okay, and you will have contact made here. Please do not worry if you do not understand fully, because we will have lot of discussions on this. Source drain, this is aluminum gallium arsenide, okay, and you will have a gate region put here, which will actually create a channel below this. Okay, in fact, you will have n plus. You do not have to take down this, because we will go into details of this. What I am trying to point out is, you can have in a high electron mobility transistor, you have aluminum gallium arsenide layer, and this will be heavily doped, this will be very lightly doped. In the case of MOSFET, if you recall, this is a oxide layer, and this region will be inverted. In this case, this whole region will be depleted, because it will be made very thin, and instead of oxide you will have this layer, okay, and this n plus layer will donate electrons into this region. Let us not worry about it today. This n plus region donates electrons to this. So, electrons are here when you invert, when you supply this into this region. Those electrons are in the very lightly doped region. In a MOSFET, if you recall, if you go to smaller and smaller scaling, doping in that region goes up, mobility goes down. Here you do not touch the doping on this layer, increase the doping here, which supplies electrons onto that. So, electrons are in a region which are not scattered by the dopants, very lightly doped. So, what you will get will be the electrons in this region do not suffer from ionized impurity scattering, but they will experience lattice scattering, no doubt. So, if they experience lattice scattering, what is the consequence? Mobility versus temperature. You remember, it is like that, but I cut this out because this is the mu I and this is mu L, that is scattering. So, you will have only one curve, this is removed. So, you can go to lower temperatures, go to 100,000 centimeter square per volt second mobility, okay, that is the powerful technique. Then of course, other application which I can just mention is in heterojunction bipolar transistors. You can make a NPN transistor, the N region made up of aluminum gallium arsenide, P region made up of gallium arsenide, again collector made up of gallium arsenide or Al gas, whatever it is, it does not matter. So, what you do is make the emitter make the emitter, okay, this is EMT, high electromobility transistor. We will have at least few lectures on this, discussing this. So, this is a very important device for high speed operations and its circuit applications also we will see. Now, the HBT, heterojunction bipolar transistor, N type aluminum gallium arsenide, P type gallium arsenide, N type either gallium arsenide or aluminum gallium arsenide. So, this emitter base collector, this junction is heterojunction. In fact, what happens is, all that you have done is, you have replaced the emitter instead of making with gallium arsenide, you have made a wider band gap material, L gas. The consequence of that is, I am just giving you the result, the beta of the transistor will be high, okay? You will get very high beta, and it will allow you to reduce the doping here. You will get high beta, you do not have to make this N plus, it can allow you to reduce the doping. If you reduce the doping, depletion layer will be wider, device will become faster. I will discuss that later with full detail. So, to sum up today, compound semiconductors based on gallium arsenide, aluminum arsenide, indium arsenide, indium phosphide, etc., have opened up several avenues, and devices for microelectronics. It opened up avenues for devices for microelectronics as well as optoelectronics. So, with that I will stop today. We will take a closer look into the crystal structure, etc., for these materials tomorrow, next lecture.